"35 degrees below zero. That is not a weather forecast. That is a death sentence. Unless you know something most people have forgotten. 1,000 years ago, in the darkest months of the Norse winter, a family of 8 could survive an entire season inside a structure built with nothing but wood, earth, grass, and stone. No heating system, no insulation panels, no engineered materials. And yet, archaeological evidence from sites across Scandinavia suggests these dwellings maintained livable interior temperatures even when the world outside was a frozen, screaming void. Here is what makes that remarkable. Modern energy audits of reconstructed Viking longhouses, conducted at sites including Lesre in Denmark and Stung in Iceland, have found their thermal performance comparable to many standard residential buildings constructed well into the 20th century. They did not discover this through science. They discovered it through something we have nearly lost: the ability to read the natural world with such precision that the environment itself becomes your architect. What you are about to learn is not a history lesson. It is a series of engineering decisions made by people who understood that one mistake, one crack in the wrong place, one door facing the wrong direction, could mean their children did not wake up in the morning. Stay with this until the end, because by the time we finish, you will understand 3 things that will permanently change how you think about shelter, heat, and what it actually means to build a home. Why Viking longhouses were shaped like upside-down ships, and why that shape was the difference between life and death in a Nordic storm. How smoke, the thing we spend billions trying to eliminate from our homes, was one of the most sophisticated insulation technologies of the ancient world, and the single architectural decision, costing nothing, requiring no materials, that could retain or destroy up to half the heat inside a building overnight. Let us begin where the Vikings began, not with walls, not with a roof, but with a shape. Close your eyes for a moment and picture a traditional house. 4 walls, right angles, a pitched roof above. Now imagine a storm hitting that structure at 80 kilometers per hour. The wind does not flow around a square wall. It strikes it, creating a high-pressure zone on the windward face and a violent low-pressure turbulence on the opposite side. That pressure differential pulls heat from the interior like a pump. Every crack, every joint, every gap in the wall becomes a path for cold air to enter and warm air to escape. The Norse builders understood this, not through fluid dynamics equations, but through generations of watching houses fail. Their solution was radical. The walls of the classic Viking longhouse were not straight. They curved outward slightly, bowing away from center in a gentle arc. A profile archaeologists have confirmed at the site of Trelleborg in Denmark, dated to approximately 980 CE, and at multiple sites across southern Scandinavia. This shape, known today as the Trelleborg-type plan, was not aesthetic. It was aerodynamic. Wind striking a curved wall does not find a flat surface to push against. It finds a slope, and it follows that slope, deflecting around the structure rather than compressing against it. The result is a calm layer of still air that forms naturally against the outer surface of the wall. And still air, trapped against a surface, is one of the most effective insulators that exists. The same principle is why down feathers keep birds warm. Not the feathers themselves, but the motionless air trapped between them. The roof amplified this effect. Steeply pitched, rising sharply to a high central ridge, it shed heavy snow loads while deliberately retaining a thin, even layer of snowpack across its surface. This was not negligence. This was calculated. Snow, dry, compacted snow, has a thermal conductivity low enough that a 30-centimeter layer can meaningfully reduce heat loss through a roof surface. The Vikings did not clear their rooftops in winter. They understood the snow was working for them. The longhouse itself was built long. Archaeological records from sites across Norway, Denmark, and Iceland document structures ranging from 15 to over 80 meters in length, with the majority of residential longhouses falling between 20 and 40 meters. This scale was not about status alone. Volume matters in thermal physics. A larger enclosed air mass loses heat more slowly when exterior temperatures drop suddenly. The building acts as its own thermal buffer, but volume without orientation is wasted. The longhouse was always positioned so its narrow end walls, the smallest surface area, faced the direction of the prevailing wind. The broad sides faced east and west, capturing whatever low winter sun was available. The entrance was never on the windward face. Instead, doorways were placed on the sheltered sides and almost always preceded by an extension, a small covered vestibule, a transitional space where incoming cold air could slow, mix, and lose its temperature before it ever reached the living area. Think of it as an airlock. Every time someone entered from the frozen outside, the vestibule absorbed the cold. The main hall never felt it. This was not one clever idea. It was an entire philosophy of how a structure should negotiate with its environment rather than resist it. We build walls to stop the wind. They built curves to redirect it. And while that insight alone is remarkable, it was only the beginning. Because what covered these longhouses from above was something so simple, so organic, so deeply counterintuitive by modern standards, that when engineers first studied it seriously, some reportedly could not believe it had been used for over 1,000 years. Imagine being told that the best roofing material available to modern sustainable architecture has been growing in meadows for 10,000 years. The Viking turf roof was not primitive. It was, by any honest thermal analysis, a remarkably sophisticated multi-layer system, one that addressed waterproofing, insulation, structural load distribution, and fire resistance simultaneously, using nothing but materials available within walking distance of any Norse settlement. Here is how it was built, and why each layer mattered. First, heavy wooden rafters were laid across the curved frame of the longhouse. On top of those rafters came the first critical layer, sheets of birch bark, overlapped like scales, running continuously from ridge to eave. Birch bark contains a natural compound called betulin, a waxy substance that makes the bark extraordinarily resistant to moisture and biological decay. Archaeological specimens of birch bark recovered from Norse-era building sites in Norway and Iceland show minimal decomposition even after centuries buried in soil. It did not rot, it did not allow water through. It was, functionally, a natural membrane. On top of the birch bark came the turf itself, and this is where the engineering becomes genuinely surprising. The first layer of turf was laid grass side down, not up, down. This was deliberate. The root systems of the inverted grass faced upward into the second layer, where they would grow, intertwine, and eventually bind the two layers into a single unified mass. The second layer was placed grass side up, a living surface that continued to grow, capturing rainfall, holding soil, and creating a root matrix so dense that the roof became, over time, essentially monolithic. What this produced was a roof with thermal inertia, the capacity to absorb heat slowly and release it slowly, that exceeded most conventional roofing materials. Earth does not respond quickly to temperature changes. On a winter night when exterior temperatures plunge, a 40 to 50 centimeter layer of packed turf continues releasing the heat it absorbed during the day for hours after the sun has gone down. And in summer, that same mass resists warming, keeping the interior cool without any mechanical intervention. Then winter arrived and added one more layer nobody planned for. Snow accumulated on the uneven, grass-textured surface of the turf roof and stayed there. The Vikings made no attempt to clear it. A dry snowpack 20 to 30 centimeters deep adds meaningful insulation value, the same quality that makes igloos survivable in Arctic conditions. The roof was not simply covered, it was armored, first by earth, then by snow, then by the cold itself, which sealed any remaining gaps. There was one additional property of the turf roof that is almost never discussed in popular history, and it may have been as important as its thermal performance. It was nearly impossible to set on fire from the outside. In an era of raids, conflict, and burning arrows, a roof made of living grass and damp earth simply absorbed flame. Embers went out. Burning projectiles found no purchase. The same material that kept a family warm through winter also protected them when violence arrived at the gate. One structure, multiple crises, one solution. But a roof, no matter how extraordinary, only slows the loss of heat. To survive, you need a source, and the source the Vikings chose was placed not at the edge of the room, not against a wall, but directly at the heart of everything. Every architectural decision made in a Viking longhouse pointed toward one place, the center. Not the walls, not the corners. the absolute geometric middle of the living space, where a long, narrow hearth called the langeld ran along the central axis of the hall, sometimes stretching several meters from end to end. This placement was not tradition. It was physics. A heat source positioned against a wall radiates in one direction. Outward, yes, but also directly into the wall itself, and through it, to the outside. Half the heat investment immediately begins working against you. A heat source placed at the center of a space radiates in every direction equally. The warmth reaches all four walls at the same distance. No corner is privileged. No corner is abandoned. The stones lining the langeld were not chosen randomly. Flat, dense stones, likely selected over generations for their resistance to thermal cracking, were placed on their edges around the fire pit, forming a contained channel. These stones served as thermal batteries. During the active burning hours of the day, they absorbed enormous amounts of heat. When the flames were reduced to coals by late evening, the stones continued radiating, silently, steadily, for hours into the night. This meant the fire did not need to burn aggressively all night to maintain survivable temperatures. The burning technique known informally among researchers as the lazy fire involved placing whole or half-split trunks of smaller trees alongside the active coals rather than feeding chopped firewood continuously. These large pieces burned slowly from one end, smoldering rather than flaming, consuming wood at a fraction of the rate of an open fire while maintaining consistent heat output. Before sleep, the remaining coals were raked into a central pile and covered carefully with a thick layer of ash, an insulating blanket that prevented oxygen from reaching the embers while trapping their heat. In the morning, the ash was pulled back, air was introduced, and the fire returned from what had been preserved through the night. The fire was never truly extinguished. It was rested. Consider what that means across an entire winter. A family that successfully maintained a slow coal bed through the night consumed dramatically less wood than one that allowed the fire to die completely and rebuilt it from scratch each morning. In a landscape where firewood collection was a significant portion of a family's labor, this was not a convenience. It was survival mathematics. But fire produces something beyond heat. It produces smoke, and smoke, in a sealed, inhabited space, should be lethal. Here is where the Viking solution becomes almost philosophically elegant. There was no chimney, not an incomplete chimney, not a primitive chimney, no chimney at all, by deliberate design. Smoke rising from the langeld ascended naturally toward the apex of the steeply pitched roof. There, it accumulated, forming a dense, stratified layer that hugged the upper third of the interior space. This layer was not wasted. Smoke, despite its reputation, is a reasonably effective insulator. The carbon particles and gases trapped under the roof ridge created a thermal barrier between the warm living area below and the cold roof surface above, functioning, in effect, as an additional insulating layer that cost nothing and required no materials to install. The critical engineering challenge was maintaining the boundary between the smoke layer and the breathable air below. This boundary, call it the smoke line, had to remain consistently above human head height. The longhouse roof was designed with this constraint in mind. Wall height, roof pitch, and total interior volume were calibrated so that under normal fire conditions, the smoke layer remained above approximately 2 meters from the floor. People lived, moved, worked, and slept beneath it without respiratory distress. To allow excess smoke to escape, adjustable openings, referred to in historical sources as yori, were positioned at the roof ridge. These were not fixed holes. They were controlled vents, operated from the floor level using long poles that could be opened or closed depending on wind conditions, fire intensity, and interior smoke density. On calm days, they opened wide. During storms, they were partially closed to prevent backdraft while still allowing enough draw to keep the smoke layer elevated. The beams and structural timbers exposed to decades of smoke became something extraordinary, impregnated with creosote and tar compounds that rendered them almost completely resistant to rot and insect damage. The same smoke that might seem like a liability was actively preserving the structural integrity of the building. Longhouses with well-maintained fire systems could remain structurally sound for generations. And in the space directly beneath the roof, that warm, smoke-filled attic zone that no one slept in, hung the winter's food supply. Strips of fish, haunches of meat, rounds of aged cheese, slowly, continuously cold smoked by the same fire that heated the hall below. The preservation system and the heating system were one and the same. One fire, one smoke stream, 4 simultaneous functions: heat, insulation, structural preservation, food storage. This was not primitive engineering working despite its limitations. This was integrated systems thinking, the kind that modern sustainable designers spend careers trying to achieve. And yet, all of this warmth, all of this carefully managed heat, would evaporate by morning unless people knew exactly where to position themselves within the space. Which brings us to something the Longhouse did that almost no modern building bothers to attempt. It created a precise thermal map of its own interior, and every person inside knew exactly where they belonged within it. There is a moment, walking into a cold room, when your body instinctively moves toward the warmest part of the space. The Vikings did not leave that instinct to chance. They engineered it. The interior of a Viking longhouse was not a single, undifferentiated space where everyone found their own comfort. It was a precisely layered thermal environment, a vertical gradient of temperature that ran from the cold earthen floor all the way up to the hot smoke layer beneath the roof. And every element of the interior was designed to position people within the warmest band of that gradient. The floor was always the coldest zone. Cold air is denser than warm air. It settles. It pools. On a night when the longhouse interior averaged perhaps 15 degrees Celsius at seated height, the temperature at ground level may have been several degrees lower, and on the earthen floor itself, lower still. Anyone sleeping directly on the ground was surrendering a significant portion of the warmth available to them. The solution was elevation. Running along both long walls of the hall, raised wooden platforms called palir lifted the living and sleeping area approximately half a meter above the floor level. This modest elevation, less than the height of a standard chair, moved occupants out of the coldest air layer entirely. The temperature difference between floor level and platform level in a well-managed longhouse interior was not trivial. It was the difference between genuinely comfortable rest and a night spent shivering. Beneath the platforms, the space was not wasted. Firewood, tools, household stores, everything that needed to be kept dry and accessible but did not require warmth was stored in this cold zone. The architecture had no unused space. Every cubic meter served a function. On the platforms themselves, the sleeping arrangements pushed thermal efficiency even further. Enclosed wooden sleeping compartments, box beds built directly into the platform structure, with solid wooden sides and a curtain or hinged panel across the opening, allowed individual occupants or pairs to create a personal microclimate entirely separate from the hall's general temperature. A person who climbed into one of these compartments and drew the curtain closed was no longer heating the entire longhouse with their body heat. They were heating a space approximately the size of a modern single bed. Their own metabolic warmth, the roughly 80 watts of heat a resting human body continuously produces, was sufficient to maintain a noticeably warmer environment within the enclosure through an entire night. This was, in effect, the world's first private bedroom, not defined by walls and a door, but by a wooden box and a curtain. And it was invented not for privacy, though privacy was a consequence, but for thermal survival. The walls behind the platforms were rarely left bare. Woolen hangings, woven textiles, and animal skins were suspended against the interior wall surface, leaving a gap of several centimeters between fabric and wood. That gap, sealed on 3 sides by the platform, the wall, and the hanging, trapped a layer of still air. Still air, as we have established, is one of the most effective insulators available. The wealthier the household, the more elaborate these hangings. But even the coarsest undyed wool performed the same thermal function. Decoration and insulation were, in the longhouse, the same investment. Now consider what was conspicuously absent from these walls. Windows, not small windows, not inefficient windows. In most longhouses, essentially no windows at all in the conventional sense. No openings designed to provide a view of the exterior or to admit significant quantities of light. This is difficult for a modern mind to absorb. We associate windows with quality of life, with connection to the outside world, with the fundamental human desire for natural light. The Vikings understood all of this, and they chose warmth instead. A window is a thermal hole. Even a small opening covered with a translucent membrane, ox bladder, oiled linen, thinly scraped horn, or thin sheets of translucent stone such as selenite, transmits cold far more efficiently than a solid wall. The materials available in the Norse world for covering window openings provided minimal resistance to heat transfer. Every opening was a liability. Light entered the longhouse through the adjustable roof vents, through the smoke openings, and, most significantly, through the entrance doorway when it was open during daylight hours. During the brief winter days of high-latitude Scandinavia, where the sun might remain above the horizon for only 5 or 6 hours, this was considered sufficient. Life that required fine visual precision, detailed textile work, carving, repair of small equipment, was scheduled for those hours, or for summer. At night, the interior was lit by the Langeld fire and by small oil lamps burning animal fat. The light was dim, the shadows were deep, and the temperature was survivable. When darkness came, wooden shutters, lined with felt, with skins, with whatever dense fabric was available, were closed across every opening and sealed as tightly as possible. The house turned inward, it sealed itself, and the heat accumulated through the day's fire was held within that sealed volume until morning. Darkness was not deprivation, it was strategy. But all of this, the platforms, the box beds, the sealed shutters, the carefully managed fire, rested on a foundation, literally. And if that foundation failed, if moisture entered from below, if the ground beneath the house stayed wet through winter, then every thermal advantage described above would be undermined by the one enemy that cold and damp share in common. They would take the house apart from the inside. The most dangerous thing in a Viking winter was not the wind, it was water, specifically groundwater. The slow, invisible migration of moisture upward through soil, into wood, through floors and foundations, turning solid structural members soft, drawing heat from the interior at a rate no fire could compensate for, and eventually collapsing the entire thermal system from below. The Norse builders were fanatical about drainage, not as an afterthought, as the first act of construction. Before a single structural post was set, before a single log was laid, the entire building site was excavated down through the topsoil, that soft, porous, moisture-retaining upper layer, to a more stable substrate beneath. The excavated area was then filled with successive compacted layers of large stones, gravel, and coarse sand, each layer reducing the pore size available for water movement. This layered cushion interrupted the capillary action that would otherwise draw groundwater upward through the soil into the floor of the house. Around the perimeter of the building, drainage channels were cut, deep enough to intercept surface runoff and subsurface moisture, lined with flat stones or bundles of branches to prevent collapse, and angled to carry water away from the structure by gravity alone. The ground immediately surrounding the longhouse was shaped to slope away from the walls in all directions. Water that fell on or near the building had one destination: away. The structural posts, the massive primary uprights that carried the entire weight of the roof, were treated before installation in a way that modern timber preservation research has validated as genuinely effective. The lower ends were charred in open fire until a layer of carbonized wood, essentially a form of charcoal, covered the surface that would be buried in or near the ground. Charred wood is dramatically more resistant to biological decay than untreated wood. The carbon layer creates a hostile environment for the fungi and bacteria responsible for rot. Archaeological evidence from post holes at Norse-era settlement sites in Scandinavia shows that charred post ends have survived in recognizable condition for centuries. Below each post, a flat stone was placed, a simple intervention that prevented the wood from making direct contact with soil. That single stone, costing nothing beyond the labor of placing it, eliminated the primary pathway for moisture to wick upward into the structural timber. The floor surface itself was typically compacted clay, mixed with sand and sometimes with organic fiber such as straw or animal hair to add tensile strength, beaten to a hardness that resisted moisture penetration from below, while providing a surface that could be swept, maintained, and if necessary, relaid. Over the clay, a layer of clean, dry material, sand, flat stone, or dried plant material such as reeds, provided both additional insulation from the ground cold and a surface that could be refreshed periodically to maintain cleanliness. The entrance threshold was built deliberately high, an obstacle that modern visitors to reconstructed longhouses consistently notice and sometimes trip over. This height served a purpose beyond the symbolic. Cold air is dense. It flows like water, pooling at low points, infiltrating through gaps at floor level. A high threshold interrupted this flow. Every time the door opened, cold air that entered tended to pool against the threshold rather than spreading across the floor of the hall. And moisture, slush, snow, mud carried in on boots, was stopped at the boundary rather than tracking across the interior. Now consider the site selection that preceded all of this. Because the drainage engineering described above was a supplement to site selection, not a substitute for it. The Norse did not arrive at a location, choose a flat patch of ground, and begin building. The choice of where to build was itself the product of sustained, multi-season observation. Where does snow melt earliest in spring? That ground is warmer, likely well-drained and south-facing, receiving more direct solar exposure. Where do the trees bend permanently away from vertical? That is where the dominant wind comes from, and where the end wall of the longhouse must face. Where does water stand after heavy rain? That ground will never be fully dry. Build elsewhere, or drain extensively before attempting construction. This was, in the precise technical sense of the term, passive solar site analysis. The vocabulary did not exist. The formal methodology did not exist. But the practice, reading a landscape across multiple seasons before committing to build, produced results that modern architects trained in passive solar design principles would recognize immediately. The longhouse that resulted from correct site selection required less firewood to heat, experienced less moisture damage, lasted longer, and provided a more stable interior environment than one built on a poorly chosen site with superior materials. The ground chose the house as much as the builder did. And once that ground was prepared, once the foundation was laid and the posts were set and the walls began to rise, the material of those walls carried its own extraordinary story, one that combined structural engineering, thermal physics, and a form of biological preservation that researchers are still studying today. A wall has one job: stand between the people inside and the world outside, and make that boundary as thermally impermeable as possible, while remaining structurally sound under wind pressure, roof weight, and the occasional Norse winter storm that modern meteorologists would classify as extreme. The Vikings built walls that did this job with dramatically different materials depending on region, because they understood something contemporary construction sometimes forgets. The best building material is always the one that exists abundantly where you are building, not the one that requires transportation across distances. In forested Norway and mainland Scandinavia, the primary method was post and plank, vertical split logs, halved lengthwise, flat face turned inward. The rounded exterior presented a naturally curved surface to wind and rain. Dense, resinous pine or oak at 20 to 30 centimeters thickness provided meaningful thermal resistance, modest by modern standards, but significant against the alternatives of the Viking age. The gaps between planks were the critical vulnerability. Any opening, however narrow, becomes a pathway for wind-driven cold under sufficient pressure. Norse builders addressed this with a material that deserves far more recognition than it receives: sphagnum moss. Sphagnum, peat moss found abundantly across northern European bogs, is, in retrospect, a nearly ideal caulking material. It does not decay. It expands when wet, self-sealing gaps more tightly precisely when conditions demand it most. It carries documented antimicrobial properties that inhibit the fungi and bacteria responsible for wood rot. Packed forcefully into every joint between wall planks, it produced a wall surface effectively airtight under normal wind conditions, not because the wood was impermeable, but because the biological material filling every void expanded, adapted, and held its position for years without replacement. Where moss was scarce, hemp fibers soaked in pine resin served the same function, hardening over time into a semi-rigid seal resistant to both moisture and air infiltration. In Iceland and the treeless coastal Norse world, where timber was scarce and imported at significant cost, an entirely different and arguably more effective system emerged. The double stone wall with earthen core, two parallel stone faces, separated by a cavity ranging from 60 centimeters to over a meter, packed densely with earth, gravel, and turf. The resulting composite wall reached thicknesses of 1.5 to 2 meters in archaeologically documented Icelandic examples. At that thickness, earth does not simply resist heat transfer. It eliminates rapid temperature fluctuation entirely. A midnight temperature plunge outside is simply not felt inside until well into the following day, by which time the interior fire has had ample time to compensate. These walls survive in Iceland today. Turf farmhouses of the Icelandic highland interior, built on principles directly continuous with Viking-age construction, remained in active use as primary residences into the early 20th century, not as historical curiosities. As functional homes in one of the harshest inhabited environments on Earth, where neither timber nor stone was abundant, wattle and daub provided a lighter, faster alternative. Woven branch frameworks coated on both faces with clay mixed with sand, straw, and wool fiber. Straw prevented cracking. Wool added insulation within the wall matrix itself. These walls were less thermally massive, but could be repaired in an afternoon and performed adequately within the broader longhouse system. Regardless of construction method, the interior face almost always received one additional layer that is easy to overlook and disproportionately important. Wooden paneling set against the wall with a deliberate gap of 5 to 10 centimeters between panel and surface. That gap of enclosed, still air functioned as a thermal break, interrupting the conductive pathway between cold outer wall and warm interior. The same principle as modern cavity wall insulation, implemented with split planks and wooden pegs, approximately 8 centuries before building science formalized the concept. The paneling also served a psychological function that should not be dismissed. Cold stone is a constant tactile reminder of the temperature outside. Wood, even at the same temperature, feels warmer due to its lower thermal conductivity. In an environment where the psychological weight of a long, dark winter was a genuine threat to a household's functioning, that felt warmth was not a luxury. It was part of the survival system. Where the landscape permitted, the exterior walls were banked with earth and turf, sometimes nearly to the eaves. The building partially disappeared into the terrain. From a distance, a well-established longhouse could appear to be a low, natural hill, distinguished only by smoke rising from its roof vents and a worn path leading to its door. One wall, 3 construction methods, multiple layers, a living exterior. And surrounding all of it, not as backdrop but as an active thermal system in its own right, the settlement itself. No longhouse survived a Norse winter alone. This is almost literally true, not as metaphor, but as thermal physics and social structure operating in concert. A single building, however well constructed, is exposed on all faces to wind and cold. One fire, however carefully managed, is a finite resource requiring continuous attention and steady fuel supply. Now multiply that building by 8, 12, or 20, and arrange them not randomly, but with deliberate attention to how wind moves across a specific piece of ground. The Norse settlement functioned as a unified thermal system. Outbuildings, barns, storage structures, workshops were positioned on the windward perimeter, not because they were less important, but because they were less temperature sensitive. These structures absorbed the first impact of incoming storm wind, reducing its velocity before it reached the residential longhouses within. The uninhabited walls of a barn facing a winter gale were doing thermal work, not for the animals inside, but for the families sheltering behind them. The spaces between buildings were calibrated. Too narrow, and the gap becomes a venturi, a channel that accelerates wind rather than blocking it. Too wide, and the shelter effect disappears. What developed across multiple generations of trial created protected courtyards where wind velocity was meaningfully lower than in the surrounding open landscape. Snow drifted against outer perimeter structures rather than residential walls. The settlement breathed, but in calm air, not in the full force of a Nordic storm. The thermal logic extended directly into social structure. Multiple families sharing a single longhouse was not poverty. It was the mathematics of heat. One large fire heating 20 people is dramatically more efficient per person than 5 separate fires heating 4 people each. The bodies of 15 people sleeping in an enclosed space generate approximately 1,200 watts of continuous metabolic heat, not negligible in a building that would otherwise need that same energy from burning wood. Community was, in the most literal physical sense, a heat source. The obligations community created, contributing firewood, maintaining the fire through the night, sharing food stores when a neighbor's ran short, were not merely social norms. They were thermal engineering expressed as culture. The society that survived was the one that organized itself to conserve and share heat, as efficiently as it organized itself to produce food. Expulsion from the community in winter, reserved for the most severe violations in Norse law, was not exile to a distant land. It was removal from the shared warmth of the settlement, left to manage alone in landscape that could reach 30 degrees Celsius. The law understood what the physics demanded. Outside the circle of shared warmth, a human being does not last long. This reframes the Viking concept of community entirely. It was not cultural preference or social instinct. It was survival infrastructure. The warmth they shared was not metaphorical. It was actual, physical heat produced by bodies and fires, pooled and conserved through every wall, every roof, every carefully placed building, into a system that kept people alive through conditions that would defeat a modern person within hours of their heating failing. They did not build homes and then form communities. They understood that the community was the home, and the walls were simply the boundary where it ended. We have now walked through every layer of a Viking longhouse, the curved walls that redirected wind rather than fighting it, the living roof that grew stronger every spring, the fire at the center of everything, never extinguished, never wasted, heating the hall and smoking the food and preserving the timber simultaneously, the smoke layer that became a thermal ceiling, the sleeping compartments that turned a single human body into its own heating system, the foundations engineered against moisture, the walls packed with moss that sealed tighter in the rain, the settlement arranged so that every building sheltered every other, and every family's warmth contributed to every neighbor's survival. None of this was written in a manual. None of it came from equations or laboratory validation. It accumulated across generations, through observation, through failure, through the specific intelligence that develops when being wrong means your children do not survive the winter. And here is the question this forces us to ask. We live in an era of unprecedented thermal technology, spray foam insulation, triple glazed windows, smart thermostats, heating systems burning fuel at efficiencies above 95%. And yet energy poverty is a documented, growing crisis across the Northern Hemisphere. Families in modern insulated homes choose between adequate warmth and adequate food during winter months. Buildings that should be thermally superior to a Viking longhouse in every measurable respect are failing the people inside them. Not because the technology is inadequate, because the thinking surrounding the technology has been abandoned. The Vikings did not have better materials. They had better thinking. They understood a building not as an isolated object, but as a node in a network, connected to its terrain, its orientation, its neighbors, its community, and the specific behaviors of the people living inside it. Every decision referenced every other decision. The roof informed the wall system. The wall system informed the foundation informed the site informed the orientation, and the orientation informed the near absence of windows, which informed the interior arrangement that placed 15 people close enough to a central fire that their own bodies became part of the heating load. It was not a collection of good ideas, it was a system, and systems make each component more effective through its relationship to every other component. That is mastery. This mastery was not lost because the knowledge was destroyed. It was lost because the conditions that made it necessary were removed. When gas heating became cheap, the incentive to understand your building's relationship with its terrain disappeared. When electric light reduced the thermal cost of windows, the discipline of managing interior light vanished. When individual ownership replaced communal living, the thermal logic of shared warmth became socially invisible. We did not forget because we became less intelligent. We forgot because we believed we no longer needed to remember. That belief is now being tested. Energy costs are rising. The passive solar design movement, gaining serious traction since the 1970s, is, in substantial part, a rediscovery of principles Norse builders applied intuitively 1,000 years ago: the curved wall, the thermal mass, the site orientation, the buffer zone, the shared warmth. None of these ideas are new. They are very, very old, tested not in laboratories, but in the most unforgiving environment available. A Norse winter, without backup heating, where failure meant death, and success meant leaving descendants who remembered exactly how it was done. The longhouse did not merely shelter a family from winter. It was the argument, made in wood and earth and moss and fire, that human intelligence, applied with patience and humility to the conditions of a specific place, can create warmth from almost nothing. We still have the materials, we still have the technology. The question is whether we still have the thinking. What part of this ancient system do you think we most urgently need to bring back? Leave it in the comments. And if this kind of deep history resonates, the next exploration goes somewhere equally unexpected. Because the people who built these longhouses also built something else. Something that moved across open ocean in conditions that should have destroyed it. The ships are next.